So in the last video we left off talking about two-dimensional center of mass, where you get an x center mass, a y center mass, and then add them vectorially that way. But oftentimes, especially in the real world, objects are not point-like objects, and so we have to deal with how to handle at least uniform objects. If the object is not uniformly dense, then really hard. Too much stuff going on, at least for a non-computer like object to try to figure it out. But if the objects are uniform density, nice sort of disks made of maybe like certain metals that might be uniformly dense, then it's quite a bit easier to figure out the center of mass. Or like the meter stick. Hopefully the wood in the meter stick is uniformly dense, although not always the case if there's a knot in the wood or something like that. But you can see when you have basically a solid plate, disk S is now still inside the entire disk. C is called the composite, meaning like it's disk S and P together, so you can almost think of it as this is not a separate disk. Then the center of mass of C, the whole thing, would obviously be in the geometric center, which is the very center of the circle. And notice disk S, the center mass of disk S, is in the geometric center of circle S. But the center mass of P, which you can see P up here by itself, where S is removed, that has to be shifted over this way slightly. And so how would you figure out how far over this is if these are not point-like objects? Some shapes are easier to do than others. Like if we had rectangular shapes, that's easy. For a circle, you have to know a little bit about geometry. This is not something you'd ever have to memorize or probably even use. But you can see that the geometric center, or the centroid, of a semicircle is shifted from the center right here of the circle by this distance, which is 4/3 r over pi. And so how you'd want to handle this, let me do a fresh screen here. I would break this up into two objects. We got the semicircle here, where the center mass is over here, 4/3 of the radius divided by pi. And then I would break it up into, well, over here it gets tricky because you got this piece here, which, well, this okay, here's what you do. You have the center mass of this semicircle, which is from disk S, minus the center mass from this, what do they call it? This quarter circle. So the center mass of a quarter circle is just over 4/3 r over pi, up 4/3 r over pi. Anyway, I'll be doing a sample problem where it's a little more easier in terms of being a rectangle. One of the sample problems coming out, I think it's the first or second one, and so that'll be more evident. But to make a long story short, when you're dealing with objects like this, what you do is you break it up into more manageable pieces. So for example, I would definitely break this up into a big semicircle here, and then probably break it up into these pieces here, and try to find the geometric center of these pieces. Then what you can do is find the area of these. So this is half of the area of a circle, and treat that as the mass of this piece, and then find the area of this piece, which you could do like essentially a quarter circle minus the semicircle of S, and that would give you the area of this, and use that as the mass, and that will help you find the center mass of the whole thing. But again, I'm going to do a sample problem, so this is just the only other picture I could find in the book that had a uniform sort of shape. Yeah, so that's what I recommend for that. Now going on to concept 2, momentum. It's a pretty basic concept. Momentum is mass times velocity. So you take any mass and give it a velocity and it has momentum. If you have someone throw something at you with a slow speed, and you catch it versus throwing it at you at a high speed and you catch it, you'll definitely feel the difference in momentum when you catch it. You're not actually feeling the momentum, you're feeling the impulse, which we'll learn later in 9b, chapter 9b. But regardless, to say momentum is sort of a quantity that moving objects can have. If an object is not moving, if velocity is 0, then no momentum. And because there's velocity in here, momentum is a vector. So you can't just add momentums up like numbers. If they're going in different directions, you have to add them up like vectors. You got to do components and all that stuff. But yeah, it's a pretty basic concept. And as I mentioned in the first video, there is no unit. So for example, F equals ma, right? The unit for a force is a Newton. But a Newton, you can think of it as more fundamental or smaller units. A Newton is actually a kilogram, and that's from the mass, times a meter per second squared, and that's for the acceleration. So this is also a unit for Newton, right? But momentum does not have its own unit. It's just a kilogram for meter for mass and meter per second for velocity. So there is no special. I guess you can make your own up if you want, but no one's going to know what you're talking about. So just call it a kilogram meter per second. And that's it for the second concept. Now, getting into the third concept, we take momentum and we talk about the momentum at the beginning of a situation in a system and compare it to the momentum at the end of a situation in a system and realize that the overall total momentum doesn't change. So for example, let's say we have a 8 ball and a cue ball, and you shoot the cue ball at the 8 ball. So the velocity of the 8 ball is 0, so that term would go away, but the cue ball has an initial velocity. And we could assume that these have the same mass. So what we could do is rewrite this. M, we'll just call the mass of any ball, since we'll assume they're the same, times V initial of the cue ball, plus 0, because the momentum of the 8 ball is 0. That's going to equal M times V final of the cue ball, we'll call that 1, plus M V final of the 8 ball, we'll call that ball 2. If we had other balls in here, we would just do plus 3 M3 V3 initial plus M3 V3 final and go from there. Now you can see we're shooting this at an angle. In fact, the whole deal with pool or billiards is that you play with angles. So you may actually only glance 8 on this side and cause 8 to go off that way, whereas the cue ball goes off maybe that way, right? So as you can see, there's a bunch of crazy angles. So we're going to do everything in components. We have to break it up into x momentum and a y momentum, and basically do pix equals pi pfx, and p initial y equals momentum final in the y direction, and go from there. System of equations, you know how it all works. And that's conservation of momentum. Essentially, momentum in a closed system, the total momentum is a constant. It can transfer from one object to another, but you can't lose momentum, and you can't gain momentum from nothing. As you know, in the real world we have friction, thermal energy, and so that changes things a little bit, but we're not going to deal with friction in these problems. So that's it. And rocket equations, this is the last concept. I think I can fit this in this video. So R is the rate of mass change, rate of change of mass change. The book puts it better. I don't have the book right in front of me here. Actually, I do. Let me pause it. Yeah, for rocket they call it fuel consumption rate. Same thing as what I was saying, but yeah, the fuel has mass, and so if the fuel is consumed, then the mass is changing and getting less. VREL is the relative speed of exhaust, the fuel exhaust to the rocket. And this doesn't have to be a rocket, this could be anything that sort of uses this concept. And that equals the thrust force that the fuel exerts in the rocket. That's how rockets work. You got Newton's third law, right? Here's a rocket. And rocket pushes fuel out this way. Newton's third law, fuel pushes rocket up that way with an equal and opposite force. So that's the thrust force. Then we have the second equation where the change in velocity is VREL, it's the same VREL as in this first equation, times the natural log of the initial mass divided by the final mass. So this is essentially comparing 2 points in time. So let's say the rocket at liftoff, right when the fuel starts burning, has a certain mass, and then 10 minutes later it would have less mass because it's burned a lot of fuel. And so you could figure out, and then you know the velocity right at launch would be 0 too, so that initial velocity would be 0. But we could use it to figure out the velocity of the rocket 10 minutes later. And it's not quite a straightforward relation because the mass is continually getting less and less over time. So, yeah. And that's it for this. Not a lot to talk about in terms of the concepts, although more things will become clear as I do some of the sample problems. So please watch those. Also, actually, there's a problem number 8 in your book with the soda can and the soda leaking out the bottom. I couldn't really find a good sample problem to do for that one, so I'm just going to give you some hints. So you definitely want to watch the video where I give you hints for problem 8. In fact, if you ask me a question about problem 8, I'm going to ask you, did you watch the video? Did you watch the video? Okay, bye-bye.